I really need to make it right. Energy, I overdose. Cause I'm ready to reload. I need it one more time. But baby, then again twice. But I don't know if I'm ready to let go. I'm gonna have you one more time. I'm gonna hit it one more night with you. With you. I am committed cause I know it's you I want. Hope I'll never see you go home. I'll come along.
I'm gonna have you one more time. I'm gonna have you one more night.
I wanna get you one more time. I really wanna cross the line. I do it all before I die. I wanna get it on tonight. I wanna get you one more time. I really wanna cross the line. I wanna get you one more time. One more time. One more time. One more time. Ooh, this time I wanna take it slow. I don't need my phone. I know how to picture in my mind the nights with you.
All right, hello everybody. I am back today, as promised yesterday, at the end of the earlier stream. I'm going to try another of the nightmare challenges. In particular, we're going to work on the Boston Key Party 2016 Simple Calc challenge. This is the first challenge in some new category that is buffer overflow static. I guess maybe static meaning the buffer is part of the memory that's in like the data segment that's predefined by the ELF binary, or could be the same in a PE, rather than a buffer that is. We did stack buffer stuff for the previous challenges and exploited those by overflowing to elsewhere in the stack frame, either first a variable in some of these ones, then overflowing the return pointer to point to a different function in these ones. And in the last ones, we overflowed, and in the buffer, we wrote our shellcode and then overflowed the return pointer to jump to our shellcode on the stack. So now, I guess the term static refers to they've got some fixed buffer in the data or BSS segment, or section rather. And so we're going to overflow that in a way which, I don't know. It depends on where that's located. Maybe we could overflow into the global offset table procedure linkage table stuff, and then trigger it to call a different function than the original code was intended to call, because we've overwritten it with a pointer to some other place. That's one possibility. Maybe we just overflow into some other data which it is looking at in order to decide, to pop a shell. Like, there's a few different things that could happen. So I'm assuming we'll go with the simplest one first, and then they will get a little bit more complicated as we go. And the next category is dynamic, where those will be presumably memory buffers that are allocated with malloc, or just some dynamic memory on the heap. And yeah, but I think probably, unless this goes really quickly, I think I only have time for this one. So I'm gonna get to it right now. I've already copied the binary. We can do file on it. It's a 64-bit ELF and not stripped. That's helpful. What do we have for security settings? We've got partial rel row. That would probably prevent us from overwriting. Well, that's like relocation stuff is read-only, I think. But that might still cover like the PLT and GOT. Hard to say. No stack canaries, but that probably won't come up if this is not a stack related challenge. No PIE. So our addresses for like the base address for the segments should be the same every time, which might be required. Maybe, I mean, if we can't overwrite anything on the stack, then getting it to return to shellcode that we put into a statically allocated buffer seems unlikely, but I don't know. This is sort of in a category of buffer overflows that I'm not sure I've done much with. So we'll just have to play it by ear, see if anything pops out. This is a bigger binary than the earlier ones because radar is actually taking a meaningful amount of time to do its analysis. I'm going to ignore the analysis errors for now. See what we have under main. Oh, you know what? I didn't run it. So I'm going to actually quit out and we'll just run it. Can we do that? No? Okay. Alright. We'll do, wow, interesting. 3? What is, do they want us to type it in as a word? No. What is, alright, I cheated a little bit by looking at their run through here where they type in 50 and that seemed to work. So let's see if 50 is acceptable. That's so weird. There's some minimum on that. And it segfaults after that. Interesting. I mean, it's just fairly broken application on its own. Okay. So it is presumably using a statically allocated buffer to store whatever information is needed for these calculations. And if, I guess if we give it a number that's too large for the amount of space it has, 50 times whatever the size of a given element in that array would be, if that's larger than the buffer space that they actually have, or if we simply, the buffer space that was actually allocated by the compiler. So if they did something like this in C, static calc struct or whatever 50, something like that, and then we give it 60 calculations or anything above 50, and it just blindly writes to it without checking the length, then we could overrun it. Okay, that's the first thing I'm going to look at. I should really learn how to save analysis results in radar, because I feel like maybe I'll just open another terminal if I don't want to wait through all of this analysis again. It's not really that long though. All right, so we set buffer to 0 on those. We print the opening text. Then we prompt for the number of calculations, which gets stored in local 14 as a quad word, I guess. Yeah. This, is that a string? It could be D or something. That would be B, right? Yeah, maybe. Okay. Let's presume that this is the... I guess that's a little weird. Like, this should be a pointer to a string, because that's what scanf takes as the first parameter. Okay, but I'm pretty sure local 14 is where that number pops up. Then compare it to 255. If it's larger than 255, then we come down here. Otherwise, if it is 3 or less, we come down here. So we need to provide a value between 4 and 254 inclusive on both sides. Okay. And then we do allocate space. So we multiply by 4. So we've got 4 bytes per entry. I don't remember what CDQE does. Convert byte to word. Oh, okay. So convert double to quad word. Do they have anything that explains what the E is about? Sign extension, I guess. Okay. Yeah, so okay, so we just are now having that in racks, and then we pass that to malloc. Racks. So our pointer to the buffer that we've allocated is 10. I wonder why this is considered static if we are doing malloc. Maybe the terminology doesn't refer to where the memory is located. Like, is it in the, allocated at load time memory versus allocated at runtime memory? But maybe it's more how the allocation is happening. So this happens once based on the number you give at the beginning of the program. Maybe that's a static sort of allocation. I don't know. Okay, so at 10 hex local variable, we've got the pointer to that buffer, which is 4 bytes times whatever number we gave. And what are we doing with? Okay, and then and 4 is our counter, I guess. And we're going to loop through that number. Otherwise, we free, once we get to the however many that was, we go ahead and free the allocated buffer, come down to return, and then we could go into this menu behavior, prints the menu, gets our response as a number, which it puts into 18. If it is equal to 1, we go to the adds function. Let's see. So let's just look at the adds approach, right? 4 is our counter, and we multiply that by 4, and then add it. So now RDX is the pointer to that element in the allocated buffer, where the element size is 4 bytes. Sounds all right to me. What do we do? Although I don't know what the adds function is doing. We should look at that in a second. Because what are we? Oh, we're moving. No. Yeah. Okay. So maybe this is a static location where the adds function stores its result. So if we look at, what did I do? No. Thought it was GQ. Okay, there we go. So the adds function is going to request the two different integers from us. It puts them at static locations, as far as I can tell. And then EAX. Okay, so if we are trying to add a number that is less than, what, 39? And some other number? Yeah, oh, it says it right here, 39. Then it is upset with us. Okay. And it just exits. So don't do that. Otherwise, and it does the check for both numbers. Otherwise, we load up both of those, call the add instruction on it, store it at this address as a D word. So, I don't know, we lose any carry behavior, I guess. And yeah, and then we print it out. So that doesn't seem like it's going to be a source of anything. I don't know. I mean, we're just storing a D word at that address. And then when it's over, we take that address and put it in our buffer of calculation results, I guess. So I definitely did get a I got, oh, okay. This is probably our issue. Yeah, because I got a seg fault when I was running it the first time, not even intending to do anything incorrect in that one. But I think this issue is we're doing a mem copy with the destination is a location on the stack, and the source is that buffer. So this does let us oh, this is going to be annoying, I think, unless I'm sort of misunderstanding what the goal is. Ideally, the goal is going to be to overflow that buffer to write the return pointer to another function that's already written in here and does, you know, a system call or something. But if we have to write a, what do I say? If we have to write shellcode into it, and the process of writing the shellcode is by going through these calculations, it's just going to be rather annoying to convert our shellcode into that format. But we can definitely do it, you know, with some Python code or something. So the exploit appears to be that we have data copied into this buffer, which is at RBP minus 40, and we could at most copy 154 times 4. 1,000 bytes rather than 64. So we could definitely overflow by quite a bit if we need to. And we can overflow to all of these variables, which we could get it to attempt to free any address we want, but otherwise it doesn't actually do any code that that uses the variables that are further down on the stack. So this will have the pointer to the statically allocated buffer, and we could override that. These two are used earlier and then no longer used by the time we get to the mem copy. I don't remember where 18 comes into play. Okay, 18's got the item, like our menu selection choice, and then 14 has the total number of calculations. So let's look. If we have some other function in here that we could call to just to what we, print the flag, for example, something of that nature, but I kind of doubt it. I think we need to write a shell code. A lot of symbols. It's all presumably stuff from, like, it's not imported, so maybe it's maybe they've statically linked in some stuff, some libc or whatever. We could do a thing that pushes just like sh or bin sh as a string onto the stack, and then loads that into RDI, and then calls system. Do we have system as a function that we can call? I don't see it, so maybe not. I don't know. They're statically linked in stuff, but presumably it didn't statically link in system because it didn't need it. That's too bad. Okay. So we could just do generic shellcode. So then the idea is we are writing to, but if we have an overflow where we can write the return pointer, but I don't know what the return pointer should be overwritten to because I don't know where. I guess we we need to have knowledge of where the stack is, or we could use one of these static locations, assuming these locations are executable for some reason. If that is the case, then one of those calculations could have instructions for a jump in it, as the as the code there, and that jump would, again, I don't know where I would jump to if I don't know where the stack is. It's gonna be tricky then. But I would have control over RBP. Does that help? Oh, I can skip. Can I? So one thing I can do when writing the buffer is skip over any of the 4-byte chunks. By typing in an invalid operation, it will still increment, and so it just won't write to that particular location. And that means I could leave some piece as the whatever the value normally would be. I need to think about what might be useful there. I think if we left RBP, then we could calculate the right offset, because it'll be RBP minus 40. And so we could overwrite the return pointer to jump to one of these fixed addresses, or not to jump to, but return into one of these fixed addresses, which has a jump. And that jump would then go, and that jump instruction would be like jump RBP minus 40. RBP will not have been, well, I guess it would not be RBP from this function, so we would have to work out what the difference is from the old RBP and the, like, we've pushed the old RBP here before setting it to whatever RSP is. So RBP will be the top of the previous stack frame, libc start main probably. So we'll need an extra offset, so it won't be exactly RBP minus 40, but it probably will be a fixed distance, fixed offset from where we want to go to, just because it's unlikely that libc start main or the whatever frame, whatever stack frame is above the one for main is going to have a different value of RBP relative to the value, like the size of that stack frame is not going to be different every time we run. So I think we still have access to figure out a good offset from RBP to jump into our shellcode buffer on the stack. So that's probably the approach that we need to take. I'm going to step away for a minute, and then when I come back, I'll get started trying to do that. Probably write a bunch of shellcode that's just int3 to trap in the debugger, and see if I can just jump into that before then we go into the process of converting the shellcode into the necessary inputs to have the addition, multiplication, whatever. I'll probably just use addition, and we could add 0 or something. Well, no, it has to be, each of those values has to be 39 or larger, I think. So we'll just subtract 39 from them. I don't know. We'll figure it out. And yeah, but before I go into that sort of tedious process, I think we just need to verify if my thinking about how we could jump into the stack allocated buffer in the first place is correct. So see that when I get a chance.
How heavy is that? Light work with the bass on the track, on my face to the back like I'm taking a slap. I need a drink but it's straight from the tap. And I'm hating the slack, couple mans run around like they hate in the gaff. Please stop talking that trash cause the vibes in the front all the way to the back. Heavy is that? Light work with the bass on the track, on my face to the back like I'm taking a slap. I need a drink but it's straight from the tap. And I'm hating the slack, couple mans run around like they hate in the gaff. Please stop talking that trash cause the vibes in the front all the way to the back.
All right, so we can get back into it. Wow, going 40 minutes already and I haven't even really gotten started. Okay. The thing that I need to do then is write a script in Python. I'm going to go ahead and leave radar open because I do this. I just don't like the level, like the. Does that help? Not really. Whatever. Okay. So I don't want to lose where I was at in radar. What we need to do is provide enough entries that the memcopy overwrites the return pointer. If we start the write at RBP minus 40, then with RBP pushed in addition, we have 48 bytes, 48 hex bytes to overwrite. Since we are doing this in chunks of 4 bytes, that means we've got 12 hex bytes or 12 hex entries that we need to provide to hit the overflow, where the last one will be an entry to one of these spots. Let's start with that. We'll just do this in stages as we, and add on to it. So I want to just trigger the return to some location. I think it would be interesting if we go back to this address rather than like that. That might be more visible in the behavior of the program to show that we did overflow and overwrite the return. We can see that we overflowed in the previous, like when I just ran it directly with the 50 value from what I got from the example in the walkthrough, because it segfaulted, so it was probably returning to an invalid address. But I want to see if we can get it to return to this function, and then if it starts saying like expected number of like if it prints the MOTD again, then we did control the return pointer correctly. Otherwise, I'll throw it in GDB and we'll see what's going on. Okay, so I want to open the process, and then what do we need to do? We need to receive until, I think it's stat. Let's go to colorization, whatever. All right, so we'll get up to there, and then we will send. Let's look at. Can I do this? Okay. Send that, and then my Python is rusty. I guess just for I in X range calculations, not X range. It's probably not even X range in Python 3. It's just range, maybe. Let's start with that, and we'll find out if I need to do something more correct. Then it's going to provide us the menu. So we don't probably need to receive before we do the send, because it's just gonna like read from the buffer regardless of what the output buffer does. But I just feel better doing it this way, so I'm gonna write it in a more interactive kind of read some and then write some and then read some and then write some kind of style. Then we will send a line to do an addition. And we want to do calculations minus 2. Is that accurate? Well, I guess we want to actually send 14 because we do need to send a calculation or provide a prompt to do another calculation for the 2 4-byte chunks that make up the return pointer location. So we'll send that, but when we go through here to send all the previous stuff, I'm gonna skip. I'm not gonna do the 2 that are gonna give us the return location because I'll have to calculate those separately. But for now, do this as just write a bunch of int3s. Like we're not gonna jump to it yet, but might as well put those in. So yeah. Then, so we will send 1 to select addition. Then the first number that we provide is going to be that gave us the colors back. That's nice. GQ. So if it's below or equal, so they have to be greater than 40 or greater. So I'll just pass in 40 for the first one. I'm assuming it'll turn those into a string. Maybe, well, we'll find out. And then for the next one, we can provide instruction minus 40, which, I don't know. Okay, and then we'll hit 5, save and exit. That should be fine. So that didn't trigger the overflow, but if we do an additional 2, so we say 20 calculations, and then that seg faults. So yeah, that's where we need to write the return address. Okay. So now we will say save until same prompt. Target dot send line, and so we send 1 because again we're going to do add. I think add is just going to be the simplest if possible. We might use subtract. I don't want to get into the weeds of multiplying unless we're like need a 0 to be written or something. So how do I want to write this? I'm going to say ret adder. In this case, we're going to do 41082 hex because that is the address for the beginning of this function. We'll send 40 again as the first operand for the add instruction, and then net adder minus 40. And lastly, so now we need to give it the give it the 5 instruction, or menu option 5, to tell it to save. Then we'll say target dot receive all, target dot interactive. Let's see what happens from this. I typoed calculations. Calculations. What line is this? Okay, so all of these need to be stringified. How do I want to do this? I think this will work. Probably need to do that. All right, that's pretty hacky, but I'm just gonna go with it. Still segfaulted. Okay, I don't want to do interactive. Receive the rest of the output. Didn't have any other output. Interesting. Maybe we should just do this manually and see what that looks like. So I don't want to, well, I'm gonna have to do it 20 times, whatever. Can I maybe I can just print all of the receive results. Then we will oh, I need to do this. It's gonna give me right. Okay. Before we go into printing all that stuff, I need to be cognizant of the fact that the that I'm putting in for the address. And the CC is actually needs to be 4 bytes of CCs. Did I do it this way? I don't think it allows this. But, right, since we're writing 4 bytes every time, I need that to be the number that we write, which is fine. And then we need to do this, but also get a 0. So first thing we want to do is just get the lower 4 bytes, which should be non-zero. I mean, it's not guaranteed to be non-zero, I guess, but I think it would be pretty rare. And since we know this is a fixed address right now, I'm not going to worry about it. But we also need to... So this is the number that we will have for that address. I think I don't have to worry about endianness because, you know, the lower half of the quad word is going to just be this value. I think we're fine there, but we do need to maybe write a 0 sequence. Just that may be involved in how we are still getting a seg fault out of this. And then if it's still seg faults, I'm going to need to print all of the stuff that we pass with send line, because unfortunately I still don't know how to get GDB working, so attaching after we do all this stuff and then looking at it in GDB, which would be ideal, is not the route that I'm going to be able to go down at this exact moment. Instead, I will output all of the input data to a text file, run GDB myself, and pipe in the text file. We will probably get to that point later on, but hopefully I can get this working without needing to get in there with the debugger. So I mean, in theory, I feel like in theory I shouldn't need to do this because we have malloc memory. Well, we did malloc, so it's not guaranteed to be 0 from that. All right. And then I want to do subtraction. And let's see if there's any restrictions on the inputs in the subtraction function, which is GU. It also wants us to give values 40 or higher. Okay, so we'll subtract 40 from 40 to arrive at the wonderful value of 0. That should be written to the upper D word in our quad word for the return address. We'll see if that solves our issue. I don't have a lot of faith at the moment. I feel like I'm gonna have to do well, that's definitely different. Let me try interactive. we got an EOF error. Oh, this was on line 34 on this one. Interesting. Can we see? So it does give us that. Why doesn't it return? Oops. Do I need to say 4, right? Okay. Yeah, I don't know why it's not getting into printing the menu again. Because we are doing calculations -2. So we're giving 20 as the value, and then 18 times we are ideally writing 4 bytes of int3, and then we are doing 1 round of an add to get this value, another round of subtract to get this. We aren't doing the copy yet because we didn't say save and exit. So why is it suddenly unresponsive? Do I need to just do an add that overflows? I mean, that should be acceptable. Let's give it a shot with an add that should overflow. 40 and yeah, it doesn't help. Oh. Well, if we add 40 in that, then what am I misunderstanding here? 39? I mean, that's weird. There must be a... What do we read into? We read a D word. Okay, not a quad word. That is my bad. So that's -1. So we need to minus, oops. Okay, so the add gets us a 0, but again, we are going to do 1 less than that? I guess so. I don't... Still seg faulting. All right, let's get into doing stuff in GDB. So how do I want to do this? Just going to create a quick function. probably can't do that in Python. Okay. Can I do right line and it will add? Just have right lines. Whatever. All right, and then of course I need to don't like it would be nice if Python had slightly better support for closures. So you can do like with open exploit. So we will do everything. Keep with the two space indentation. So we'll have f to pass in here, but it would be nice if I didn't have to write these as parameters. Like in JavaScript, I could just define the function in here and then use target and f if I defined it right here, and it would, because everything in JavaScript is a closure, it's going to access those variables. But I don't think that is the case in Python. So essentially, with okay, so now we call our special send line that also writes to the exploit file. See if that messed stuff up. Yeah. What did I mess up there? Oh, I put while instead of with. That's fun. Okay, great. Okay. So what are we doing? All right. What is this? That might be part of the problem. Nope. Oh, that should add to get us. Yeah, that should be fine. Right, it's a different number than this. Okay. So let's give this a shot in GDB. And where did we segfault in the call to free because we have overwritten that particular. Okay. All right. Fair enough. Fair enough. So what's happening is the pointer to the dynamically allocated heap allocated memory is at RBP minus 10 hex, and we are just blowing past that with one of these, putting CC in there. So we need to skip 2 of them before. I mean, we could just skip from then onwards, basically. Okay, I thought we were going to get into the skipping stuff a little bit later. Oops. Nope. All right, so total calculation still needs to be that, but how many are we going to use for writing shell code? Let's see. So 30 hex is going to be 48 divided by 4 is going to be 12. So I guess I can just say 12. So we're not actually going to calculate stuff based on that. Just say 20 then. Okay, and 12 times we do this, then another 6 times. We're gonna do we are going to send some invalid option. Yeah, that will progress us. In fact, let's try it with. Okay. Maybe we need to do 21, just so that we don't, because this quit out before it didn't necessarily do the save and return. Yeah. So because if we hit where is it? If it is not less than the number that we put in, then we just go to free and exit, and we didn't do the mem copy. So we need to put at least one more in there. Okay. So do 12, so 48 bytes of CCs, then 24 bytes are skipped. So that's, yeah, 16 plus the 8 from the pushed RBP. That should be fine, and then we write the return address. Okay, so we have interactive, but I really just want do we have a, oh, is it waiting for, it looks like it was waiting for an input for some reason. No. Yeah, because it's like, what integer? What do we have in here? So pass in 21 in each of these sequences. I don't get it. Why would this result in it still waiting for an integer? Well, we can just like see what's going on. Okay. That time it was not waiting for anything. So I don't know what the deal is, but we got 2 additions resulting in 0 afterwards. Like, I think this is the one that's going to be... Why? Maybe the printing order is weird for some reason. Doesn't seem like it should be. Well, let's try... Because I think if I only put 20, we are going to do all 20 of the calculation inputs. And so it's just going to end the program. Yeah. By freeing that memory. And we have skipped over that, so we no longer get the segfault from there. So, I mean, if we do... It doesn't really matter if we like really overrun the buffer, I think. Okay, well, we're getting a segfault, and I'm gonna throw it in GDB again. And see where we are segfaulting. So we are at address 0. So let's look at where we call memcopy. Okay. So after that call is 455. Let's run it again. So we just did memcopy. We've written all the C's. We skipped some stuff. And we're going to load RBP plus 10. Is that... RBP is 400. So 410. 400 minus 10 rather. That still is going to be down here where I think the F values would be. Well, no, we just don't see it because I really need to figure out how to make the stack print out larger. And F, I need to spend some time in between these streams actually improving the tools or improving my configuration. So what do we load into Rex? Okay. That's a 0 in there. It seems like we have fucked up with where we are putting. Like it shouldn't be. Oh. Okay. Right, because we're never actually. My whole theory about not writing certain values is incorrect. Oh, then I don't know how I'm going to solve this, I think. Fuck. We're not writing them into the heap buffer that we allocated with malloc, but it's still being copied from that buffer to memcopy. So it's whatever was in that memory beforehand. is going to overwrite everything on the stack. Ugh. So we can't retain RBP as it is, pretty sure. Unless there, there could be an issue with one of the other calculation instructions that we could exploit to get a stack pointer, link a stack pointer somehow, but I kind of doubt that is the case. I mean, the thing I could try to do just to begin with is try to solve this without ASLR. In fact, that might be why we're getting the seg fault, right? Because I have put in a fixed address. It's not PIE, so I would have thought only the stack is randomly has a random layout, has a random base address, but I don't know. Let's see if it works in GDB, I guess. So the free call is working because we're just freeing a null pointer, and free is going to do a no op when that happens. Okay. So when we get to the return, we're pushing to adds? What in the crap? Why do we have that at the top of the stack? I'm putting the wrong address in? Oh, maybe I copied it out of... Yeah, okay, that's my bad. That's why we were getting that input. Which then means that... At least I think that's why we were getting that as the remainder of the input in when we ran it with Pwn Tools. Because I had put the wrong return address in there. I forgot that we were looking at the add function. Okay, so in theory, I guess we should just oops. See if this happens again. What did I do wrong this time? Fuck something up. God damn it. Because it should show more than that. Even if it's failing to receive this. Let's change it back. Okay. It's not giving me the prompt anymore. Let's see what the first line is. All right. So that is the banner, I'm pretty sure. Yeah. So it prints out the MOTB. Oh, it's receiving. We should be receiving to the colon. Yeah, okay. So we are controlling the address, and these are fixed, but I suspect that the I suspect that the stack address is not fixed. So knowing where to jump to for that is going to be tricky. We can jump to, looks like maybe I have another viewer. Hello, if you're watching. I mean, I'm pretty sure we could jump to one of these fixed locations where it stores the calculation result from whichever operation function gets called. But what do I need to do? What code do I need to put there? They aren't. It's 4 bytes, which doesn't give me a lot to work with. And they aren't sequential. They definitely have, this is 8-8, this is B8, this is A8, 9-8. So they are like 16 bytes apart. 8-8, 9-8, A8, B8, yeah. And we are just writing a D word to them, so that's going to be zeros in between each one. So while I could, in theory, put a little bit of code in there, it's like severely constrained. I've got 4 bytes and then 4 null bytes that I need to deal with, like accept that as what it is, or I need to jump away from that. I just don't know how I would jump away from it if ASLR is on, and I don't know where the stack is, so I can't just jump to where I need to in the stack. So I'm just trying to think, like, we don't ever write any stack addresses to fixed memory. Yeah. So I could try to write some real minimal real minimal shellcode. So we've got 4 sections of 4 bytes each that we could put our shellcode into. Those sections are separated by 4 bytes of zeros. A 2-byte sequence of zeros is the equivalent of add EAX, I think, or it dereferences EAX and adds AL to it, I think. So it is, I mean, we could set up EAX to be some value so that when those instructions run, they don't impact anything. But that doesn't help us really, because we've still only got 16 bytes for instructions. We don't have to waste, in theory, we wouldn't have to waste any on a jump. We would have to waste some on setting up EAX. But like the shortest shell codes that I've seen to run SH are like 20 something bytes. So we're already too short for that if we're just putting stuff in these fixed locations. What could we do? I can't imagine it's actually as complicated as I'm making it. I have a strong urge to just turn off ASLR and get it working that way, and then read the walkthrough to see what the proper solution is. But that's kind of cheating, at least from the standpoint of me figuring out how to deal with the ASLR mitigation. So I want to think about this more and really figure out why. Oh, what was... Now that would be really annoying to deal with, but... Technically, we are storing... It's not 4 bytes of zeros, which is both annoying to take advantage of, and it is a potential hindrance. So I don't know if this is the route that I want to go, but we have a sequence. Is there anything at... oh, yeah, okay. Then 8. Oh, I guess it wouldn't mention that. Okay. Do we have anything at C? So we would have... Yeah, I don't know why I was saying 4 bytes of zeros. It would have been a lot more than 4, but what we actually have is 4 bytes with the value of the first operand, then 4 bytes with the value of the second operand, then 4 bytes with the value, the result of the calculation. Then I think 4 null bytes. I didn't see any reference to, in this case, what would be 4A8C before it repeats at 90. So we would have 4 null bytes in this scenario, and then we've got, for each of these 4 segments, we've got 12 bytes that we control the value of, but with the caveat that the last 4 bytes of those 12 is the result of the calculation of the previous 4 bytes. So, I mean, that's a rather annoying limitation to work with in figuring out a shell code that could fit in these. Yeah, that would be just too... I mean, if that's really the way to solve this, I think I don't want to do it. I would be curious to see if that, is how it got solved in the write-up, in the walkthrough. If other people solved it this way that were participating in the Boston Key Party CTF. It's just such a pain in the ass, I think, to make it so that your 4 bytes of shellcode adds with another 4 bytes of shellcode to generate either 4 bytes of shellcode that you can use or 4 bytes of junk, I guess. Maybe you just jump past that. Yeah, maybe that's how I'll do it. A jump instruction that is like a unconditional jump with an offset of, within 24, that's 2 bytes. So I lose 2 bytes for each one of those sections. So for add, we could get 10 byte, or no, sorry, we could get 8 bytes minus 2, because we're going to not care about the add result. We're going to jump past it and past the 4 null bytes. And then we get 6 bytes for each of these 4, which is just enough for the shellcode, one of these like 23 byte shellcodes that they were using in some of the previous ones. So I guess that is where we're at in the reality of this challenge. Okay. So the address that we're going to is no longer that. Instead, we're going to go to 6C 4A80. Yeah, okay. And then instead of CCs, so this is actually junk up here. We're not going to use this for shellcode because we're not jumping to the stack. But I'll just leave it as is. Or doesn't really matter. And we didn't really need to do this skipping of stuff. So maybe we just we'll just write all nulls for all 18 of these. And just stop caring about that. Okay. So we write 18 instructions that result in writing null to the result buffer. Then that'll get copied over. The free call will be a no-op because it's going to try to free a null pointer. And then we write the return address. And lastly, we need to write shell code into the static memory yeah. So I guess that's why this is a static challenge, because really we are putting the shellcode in the static locations. So not going to look at the walkthrough here, but I am going to copy the shellcode from Shellstorm that they were using, because that was like really short. It would be good if, oh, this is, we need 60, I mean, we probably don't need 64-bit, but I'm gonna see if we can do that. Where's, there we go, okay. Linux, x86 64, do we have one? Maybe we do have to use the, I don't want to reboot. Yeah, 27 bytes is pretty short, but not short enough. I guess we'll use the 32-bit. That should be fine. All right. What does this shellcode do? Let's see what the instructions are to begin with, and see if I can write it in assembly inside of the script rather than just paste a blob of binary machine code. How do I want to do this? Nope. Right. Can I guess I'll just use Vim block mode to get rid of all those prefixes. Okay, so this could be really difficult because we have to put those jumps in and we don't really have a choice where we put the jumps. So we've got 6 bytes, then we have to jump. So and if we're pushing, let's think about this. Like, can we rearrange certain things? And this is B rather than 3B. I don't know if this shellcode is going to work at all in 64-bit. I would assume that the syscalls are different than in 64-bit. Yeah. If we have a list specifically for, so B being 11, that's M on map. I don't think that's what we want. Okay. So can we rework this in a way that is most useful? So what do we have here? Slash B I N probably slash slash 2 slashes, and then 73 is probably S H. Can we put that into one push, which is going to be 1, 2, 3, 4, 5, 6, 7. Annoying, annoying, annoying. Let's think. Right, because we are using 3 bytes to put 0 to finish out that string on the stack. Whereas if we are in 64-bit, we've got an 8-byte register. And so we can throw it all in one register, one push. But what do we need to do? If we push, but we can't push the whole thing in one of these chunks, because the string is 7 bytes and we've only got 6 bytes of what you call it, 6 bytes of room before we have to jump. So, and we need 1 byte for the actual the opcode. So we can push that, then we might be able to like add Okay, so first off, I want to not use the shellcode from this one. I want to use the shellcode that they got from whoever did the pilot one, I guess. Because they had a nice short 64-bit shellcode. Let's look at this one instead. Because it's just the syscall is totally different, so I don't want to do a lot of work on this and then realize, oh, I have to change a bunch of stuff around for the syscall. All right, so they've got 1, 2, 3, 4, 5, 6, 7. Is that accurate? No, because that continues on. This is just output improperly. So it's actually 1, 2, 3, 4, 5, 6, 7, 8, 9. How's it 9 bytes? Oh, it's probably okay. It's just from D1, right? This is the opcode. Okay. So how can we deal with that? All of these are off by 1 as a result, but the output from the disassembler is not off by 1. Yeah, why is it? It's missing some bytes. That's only, so that is 24 bytes, which is exactly the amount of space that we have. If I can rearrange this to be able to insert jumps as needed. And that is a big if, because that push is just not. Or it's not a push, but it's a move into RDI. No, we don't have to be concerned about null bytes, which I think the reason that they're doing this with the negation is because of not wanting to put the null byte in there. So I'm not too concerned on that front. Okay. So what if our job is put SH into the RDI register, shift that over by 20 or not 20, 40 bits. Is that, I think that's right. Because we wanted to start at byte 5. and then we and it with the /bin/. All right. I'm going to start with this shellcode and see where we can get from there. But I just need to work out exactly how many bytes things are going to be. Okay, so we want to move RDI. What is S? Lowercase s. $73. And H is going to be 68. 6873. So that should be SH in Little Endian. And then we want to shift right, no, shift left, RDI 40. And RDI with /bin. Okay. So the slash is 2F. Why can't I insert 2F? 2F N is 6E. I 69. Oops. And then B 62, of course. And then another 2F. Okay, that is going to be too many instructions, just right off the bat. I can tell that. So let's see how many instructions that is. We've got 3 bytes of immediate data. And if we're lucky, it's only 3 bytes for the opcodes. Permanent raw. $11 bytes for that. Is that true? Really? We have, oh, okay. Okay. What I don't actually need, can I do this as EDI? Or even just DI? Okay. And I do need the 64-bit register for... Why don't we do... All right. That is 8 bytes, still too long. I really hope that this is the way to do it, and I'm not just wasting my time trying to write an incredibly space-constrained shellcode. I guess before I go too much further with this, I should try to return into that address in the first place, just to see if my suspicion about how this could work is even correct. I don't want to waste a lot of time writing the shellcode and then I can't even do the thing that would use the shellcode. So I'm going to take another break for a few minutes and then we will come back and try jumping to the, not this one, but 8.0, which is the beginning of the static memory that I can write arbitrary values to. And yeah, we'll see how that goes.
How heavy is that? Light work with the bass on the track, on my face to the back like I'm taking a slap. I need a drink, but it's straight from the tap. And I'm hating the slack, couple man stand around like the hate in the gaff. Please stop talking that trash, cause the vibes in the front all the way to the back. How heavy is that? Light work with the bass on the track, on my face to the back like I'm taking a slap. I need a drink, but it's straight from the tap. And I'm hating the slack, couple man stand around like the hate in the gaff. Please stop talking that trash, cause the vibes in the front all the way to the back.
Okay, so we will dive back into it. Before I go forward with the shellcode, I am going to let's do 6 bytes of breakpoints, and then jump forward should just be 8 bytes. And do that 3 times. No, 4 times. Giving us a total of 24 potential instructions. So, yeah, we will see. I need to set up the context. And then we'll compile the shellcode, and we need to move through this in chunks of 4 bytes. Or, yeah. So, maybe that's the phrasing. I know that you can like provide that third. Oh, well, this is just the array itself, but you can provide like a third parameter to the index operation, which is like the step amount. I guess I can just so we're gonna do like for index in range 0 when shellcode ASM 4 and print see what that looks like if we just run it that way. What is it? It doesn't like the shellcode. Shellcode contains relocations. Do I have to? I can't just say jump and then give the offset. How do I put a literal? Do that. I think that's like AT&T syntax or something, right? Yeah. All right. So let's say part 2, part 3, part 4. Let's see if this works. No? Still has relocations? Where's the fucking relocation? Offset 1F. Oh, I need to get rid of that jump at the end. Don't need that. So if we don't have the jump at the end, then that means we actually have an extra 2 bytes in that last section. So that's good. I didn't think about that. So we've got 32 bytes minus 6 gives us a total of 26 bytes. Yeah, seems right. How do you integer or slice? I don't remember how to do fucking slice. Oh, with colons, it's just its own special syntax. Okay. Because I don't need to encode it, and that's, I mean, for, okay. So why is that 0? How do I write? Do I have to manually create this? Like, it can't assemble it. The thing I did before, which had to jump to a particular label, seemed. Oh, yeah, okay. It's jumping 0 because I don't have any space in between. So that's fine. I will, but it is annoying. And I don't know if there's a good way to do that. Can I define an offset, like an actual memory address? Oh, that's looking in every wiki book. I don't need that. So gas, I don't know what the assembler is on this. Massive? Maybe. Can I mean, what fucking website in the entire world has the actual grammar for an assembler so that I can find out, you know, can I put a label that is an address? What is the syntax for doing that? Is any of that meaningful? I don't know. Just gonna. All right, what we're gonna do is it's gonna be 2 words of nothing between each one. That's just how it's gonna be. Except a word is 2 bytes. Can I say D word? Doesn't like D word. Who is the assembler for this? GNU AS, which I guess is gas. Yeah. Don't you? It's just part of bin utils, of course. No. Oh. There we go. Okay. I think I found this earlier. But we should have dot double, right? And dot quad. Because we have dot 8 byte. This really doesn't work with my dark mode plugin. Yeah, dot quad. I don't know. I was just missing it. Okay, and presumably double, but that's for a float. Yeah. Then what is this? Okay. Oh, okay. Dot skip. And dot space. They have so many ways of saying this. Okay. Is there just a way to force an address so that I don't have? I guess it doesn't make a lot of sense. All right, I'll deal with the extra spaces in there. So what I want is dot size or dot skip 8 bytes. Let's see if that works. Okay. So we've got our 2, And then the two that we can't do anything about and our two. Yeah. All right. So we want to go every 16. And what we're going to do is target.receive until, and then send line f target string 1 to do a, oh, okay, I'm not going to do this in a for loop because I need to have a different, need to do 1 and then 4 and then 3 and then 2. Looks like, okay. So what I want to do is but I don't want to send this as a string. I want to send this as the binary bytes. Hacky bullshit here. All right, so then we have a bytes version of sending a line where we are going to get shellcode assembly from 0 to 4. And then next from 4 to 8. Then we do 4, and we go from 16 to 20, 20 to 24. We'll do 3, and does that seem accurate? Yeah. We do 32 to 36, 36 through 40, and 48 through 52, 52 through 56. That'll be interesting to see what that is. Broken pipe. Let's just cat out the text, and then we start providing. Yeah. Oh, no, okay. Can I convert bytes to an integer? Because I need to need to unpack from bytes. Can I do okay, that's what I need to do. 32 and I'm just going to do it all manually. I need multiple. Oh, okay, that's my bad. And then I don't need the bytes version. I should have really thought about that more before I went ahead with like, oh, of course I need a, just do it, version that does that. So let's see how that goes. All right, that's interesting. Definitely not what I expected. What is the address we're putting in? Yeah. Okay. Gonna go ahead and run it in GDB. And I want to go to the ret. Yeah, so it's gonna jump to a bunch of int3s, which is where the add function is. That seems incorrect of GDB. So it's saying this is add +1. Which, why would that be where the add? Oh, because this is adds. What is it? Like, there's nothing here. No. Okay. What? Why did we just? So that must not be executable, I guess. Okay. I am going to try this with ASLR off, I guess, and just write shellcode into the buffer that it allocates dynamically, which then copies onto the stack and will jump to the stack with a fixed stack address, because let's run this, and then you can see, yeah, that location for the data segment, the read-write segment, is not executable. So my whole plan, I'm glad that I went through this on the int stuff. I mean, it was obviously still took a little while to do it. I probably could have gone for a much simpler shellcode just to double check to begin with, but yeah, we can't jump into those instructions or those memory locations and start executing them. So our only option, but the stack is also not executable. I don't then know what to do unless there's just another function in here that I haven't seen that does what we need it to do. I mean, that's definitely plausible, and I didn't do a very good job of exploring stuff in Radar. If that's the case, then man, I really spent way too much time on this. But yeah, NX is enabled, so we can't jump to the stack either. So the only thing I can think of is we've got, unless, I mean, I could do a ROP chain, I guess. But since that hasn't even been like that idea hasn't even come up. I don't know why we would try that, I guess. So I truly don't know how to do exploration in Radar. So we can go here. Like, I mean, if it's just some function somewhere is, yeah, not helpful to me. Try this one instead. This is nothing. I don't know why it thinks that's a function. Also don't think this is a function. I guess it, no, there's too many just null bytes in there. I don't like this doesn't, why would that ever be? Maybe there's a better way to do this, but I don't know what it is. All right. What was the one that I just did? 536. Yeah, this is tedious as hell. I'm gonna skip the one that's 3 bytes long. Doesn't seem likely to be a meaningful function. Oops. Oh, okay. I could just do this view, but again, I don't know. And there's so many functions. Like, what is the function I'm maybe wanting to make use of at this point? Where was find derivation? Why is this listed here as this address if it has a name up there? Is this one that I'm going to have to just pop into a disassembler that I am more equipped to use? Spent so much time going down paths that are not going to work at this point, and that's doesn't make me feel great about where things are at. I mean, it's just a ton of like libc functions that are statically compiled in, I guess, statically linked in. it say? Okay. Yeah, are any of these going to be interesting to me? I don't have any reason to think that they will be. I really don't know what I should be doing in this case. Did I get through all of these, or am I just going through it too quickly? I realize this looks kind of horrible on the stream, so I'm going to stop going through all of these. But yeah, it's just, it's a lot of stuff from Loop C. So, like, probably in theory, you could get a let's do that. You could get some kind of ROP chain going from this. But otherwise, there's got to be a function in here whose address we should be jumping to. But the thing is, like, that stops making it an interesting challenge. Or at least, like, not stops making it interesting, but makes it not that different from the earlier ones where we were overriding the return to go to a particular function that was already written in the code, in the binary. So, like, the bit where, we had to put the code, when I thought we had to put the code in those 4 separate, writable, statically allocated memory addresses, seemed more plausible as, like, this was a buffer overflow involving static memory, I guess. This one doesn't, like, if it's just find a function to jump to, then it does not seem like it involves static memory at all, really, because it's dynamically allocating the buffer, then it copies it to the stack to cause the overflow. Yeah. All right, I've been going at this for over 2.5 hours at this point, and I'm not at a point where I think I know where I should be going, making use of the overflow that I clearly have control of the return pointer, but getting the, remainder of the exploit of knowing what to do with that, I don't know anymore. I'm not seeing any functions in here thus far that make me think, oh, that's how I'm going to pop a shell or something. So I guess this is going to be the first one that I just go look at the write-up and see what I missed and what, this is the first in this section, so in theory this is going to be a super easy one. And I have either missed something really obvious so far and I'm going to be kicking myself, or it's going to be, a thing that I apparently just didn't want to do, I guess. This is really not how I would like to end working on these. The point is to be able to do it myself, and certainly reading through the README, I will try to go through the solution that they present so that I can get the experience of having done it, but figuring out the solution yourself is a really critical part of being able to do this stuff in a CTF or in a job or, some other scenario. But I'm just truly not seeing what I should be doing with it at this point. So let us, still just looking through this list, hoping to see something that sticks out to me. It's very possible that I've gone past whatever would be the thing to use, and it just isn't occurring to me that that's a thing, or I've missed it in the big list of stuff. But we've gotten to the top again, so all right, sort of giving up halfway giving up on this one. Let's see what I needed to do for BKP 16. So we can see that it is a 64-bit statically linked binary. The only binary mitigation is it has a non-executable stack, so we can't push shellcode onto the stack and call it. When we run it, we see that it, well, okay, if it says, I'm trying to think if there's potentially a way to jump into where the memory gets allocated from malloc. It seems unlikely, but let me run it a couple times in GDB. See if I can recall malloc. It's got to be up here somewhere, right? There we go. So let's see what we get in RAX after our various calls to malloc at main plus 188. Oops. Okay, RAX has a little bit more space. That address, interesting. It's the same address every time, actually. So malloc is just, I mean, it's calling set break, I guess, or S break, which is going to then give us memory apparently right after the BSS segment ends, or whatever. Like it's at 6C 8BE0. So, but the heap is not executable either. Yeah, so that, I don't think I can jump into that. Same deal with this. Okay, never mind. When we run it, we see that it prompts us for a number of calculations. Then it allows us to do a number of calculations. Also, it apparently won't let us calculate small numbers. When we take a look at the main function in Ghidra, we see this. Okay. Is there anything that I missed in my reversing? No. That all looks accurate. So we can see that it starts by prompting us for a number of calculations with the string expected number of calculations. It stores the number of calculations in number calcs. Then it checks to make sure the number of calculations is between 3 and 100 hex. If not, it will print invalid number and return in the program. It will then malloc a size equal to number calcs shifted left by 2, and store the pointer to it in calculations. This is the same operation as number calcs times 4. Just check out these calculations to see, yeah, I believe you about the shifting. Here it is essentially allocating number calcs number of integers with each of them are 4 bytes big. Okay? I guess that is yeah, because that's just where we store the result values. Then we'll enter a while loop that will run once for each calculation we will specify, unless if we choose to exit early. Look at the assembly code. Since the decompilation looks a bit weird for the multiplication section, we see that it's calling the moles function. When we look at the moles function, we see that it checks to ensure that the two numbers have to be equal to or greater than 27 hex. Looking at it, we see that it pretty much just multiplies the two numbers together. Looking at the other 3 calculation operations, they seem pretty similar, except for subtraction, addition, and division as the operation. Yeah. However, we can see there's a bug that resides in the option to save and exit. If we choose this option, it will memcopy to copy all of our calculations into the vuln buffer, which is on the stack. Thing is, it doesn't do a size check, so if we have enough calculations, we can overflow the buffer and overwrite the return address. There is no stack canary to prevent this. Let's find the offset from the start of our input to the return address. We start off by setting a breakpoint for right after the memcopy call, and then seeing where our input lands. So they do this is their approach to calculating the offsets is in GDB. And they get 48 hex, which will be 18 integers. Now for what to execute when we get the return address. I'll turn off my music in the background. It's getting annoying. Since the binary is statically linked and there is no PIE, we can just build a ROP chain. Oh, okay, so that really was the solution. Even though this is in the buffer overflow section, this is just, hey, do a ROP chain. Okay, well, I'm not going to read any further, because if I know that's the solution, I feel a little bit good that at least it occurred to me that that would be how you could go about this when you can overflow on the stack, but have no writable, executable memory, whether it's on the stack or some other segment, like somewhere in the heap, or the BSS data segment stuff. So given that I can see that this is now a ROP chain attack that we need to do, I've actually never done one of those, and I think I want to try to learn about that enough and do it myself before going through their walkthrough. I'm maybe a little bit annoyed, definitely a little bit annoyed that the solution to this is like something that was not even, I mean, it may have been barely mentioned as a, and if there is this mitigation in place, you might have to do this, but no explanation of what that is or how you would do it. And then they just throw you, here's a challenge, and the only way to do it is through this technique that we've not even introduced to you. Just as a, I don't know, I think I'm just looking at this project incorrectly. I'm thinking about it as a learning tool rather than just a collection of challenges where you can go learn what you need to learn somewhere, anywhere else, and then tackle this challenge. So it's just, a decently organized collection of CTF challenges if this challenge requires a ROP chain to solve it, I don't know why it's not in the ROP chain category or the ROP general category of ROP stuff. Why it's in buffer overflow. I mean, I would think that almost all ROP based exploits are going to work from some kind of buffer overflow. There's probably other ways to achieve control over the return pointer, but you then need to like write several return pointers beyond it on the stack in order to be able to execute the chain that does whatever code you need to do. So in that sense, they're all a subcategory, or mostly a subcategory of buffer overflow. So it feels weird that it's in this section. And then I'm wondering, like, are all the rest of them going to be ROP? And so, in any case, I'm going to stop the stream here. It's been about 3 hours that I've spent on this, going down the wrong path. Most of that was my fault, just for in the beginning believing an incorrect thing about how the code was working with the mem copy, and something that was really should have been a lot more obvious, but I think what I wanted to believe allowed me to think that the challenge was simpler than it was, and so I went forward with that until it became kind of untenable to keep thinking that was the case. And then going forward with an alternative, which I probably, if I had just looked at the memory map permission stuff, virtual memory permissions, I could have seen that what I was attempting to do wasn't going to be possible anyways. So that's a good lesson, is, remember to look at the sort of indicators that are around and available to you, whether the path that you're going to embark on is actually workable at all. If you can see something that says that's never going to happen, then I don't need to spend an hour trying to work up some, annoying, like, mini shellcode setup. Mini shellcode, like really space constrained shellcode, and putting it in that structure and stuff. So most of the time wasted is really entirely on me and my own methodology that needs improvement. But I think a little bit is still just at the end, where I was like trying to think of any other way that this could be done but ROP, and effectively coming up with nothing. I feel a little bit burnt, but that's mostly not on them. I just have already gone over the concerns that I have around the organizational choice of putting it in here. So yeah, I will come back with a stream. It's probably tomorrow. This one is already longer than I think I really have time for today. I have a lot of other stuff that I got to get done today that I'm going to go to right now. But tomorrow I'll come back. I'll try to do some research before the stream of a little more research on ROP. I understand what the technique is, but definitely some research on how, like, what tools I have available, if there's anything in Pwn Tools directly, or if I need to go download some other thing to help me find ROP gadgets and build a ROP chain from them using this binary. There's definitely a lot of stuff with it being statically linked in with a lot of libc stuff, I guess. So I shouldn't have any trouble finding the ROP chain, and certainly the fact that that was in the walkthrough. Yeah, it's not a dynamic executable. So lots of stuff in there. And since it's not PIE, we know what the addresses are. We don't have to worry about dealing with ASLR leaking something in order to generate our ROP chain, the addresses for it. So yeah, hopefully I will be doing that tomorrow, and I can get past this one, and we'll see if that's just the thing that I need to do from here on out, and all the other challenges. Certainly, if we have a format string thing, that's not gonna probably need ROP, because you can overwrite. Well, I don't know. I guess if there's an X bit on there or something, like the fact that you can overwrite stack address memory isn't going to be meaningful. So yeah, the way to think about it for me, I guess, is just, given the existence of these mitigations that can be just turned on automatically and really should be turned on automatically with any modern system, when you're building your executables, then ROP chain based attacks, exploits are the thing that you got to do all the time because you don't have any other options. And then there are mitigations around ROP, apparently. Like any mitigation, they're not 100% successful, but I don't know if those will come up at all in this nightmare course. All right, thank you for watching. If you are watching this stream, if you're watching on the recorded VOD, appreciate it, I guess. You can check out my Twitter account, twitter.com/hamledonline. Really, I retweet a lot of stuff about politics rather than maybe a little bit of stuff about hacking and computers, so I wouldn't worry too much about that. But you can certainly friend me or whatever it is, follow me on Twitter, and let me know that you've watched the stream, and I'll probably follow you back if I can. I've kind of at the limit of how many people I can follow, but I'll go through the list and see if I can get rid of some follow that I don't need or care about anymore and give you a follow instead. And you can go to my GitHub. If you go to hamled.dev, that'll take you to my GitHub. Has my email address on there if you want to just contact me through email. Yeah. All right, I am going to end the stream now. Thank you very much.